Hello, am I audible? So, good morning everybody. Myself Jess, and since last 4 or 5 days we have been hearing a lot about epoch of reionization and its importance and how and why to measure. So, I will be talking about the calibration requirements for EoR observations, where we shall discuss the effect of time and frequency correlated gains in estimating the 21 centimeter power spectrum using visibility correlation based estimators. So this work has been done along with these peoples. Samir has already given a detailed overview of the actual measurement process and the real life problems which arises in the observation of the 21 centimeter signal using various interferometric observations. So here we have these are the various interferometers which are trying to detect the 21 centimeter signal, and the quantity these interferometers measure is called the visibility, which is the Fourier transform of this sky brightness distribution multiplied with this antenna primary beam. So from these visibilities we can calculate the H1 21 centimeter power spectrum using visibility correlations. So the observed visibility which we get from the interferometers is not only the sky visibility, but it is the gain multiplied, which multiplies the sky visibility. On top of that, we also have the thermal noise. These noise are uncorrelated Gaussian variables which are usually very large, and we can correlate these sky visibilities to get the power spectrum in this way. These sky visibilities has two components, one coming from our target, which is 21 centimeter signal, other is the foregrounds. Foregrounds are usually 3 or 4 orders of magnitude larger compared to the 21 centimeter signal in temperatures, brightness temperatures. The major component of the foregrounds are galactic diffuse synchrotron emission and extragalactic point sources. There are other components as well. So to detect the 21 centimeter signal out of this sky visibilities, so we need to subtract these foregrounds. So foreground removal is essential, and we also have to correct for these gains. So for solving these gains, we perform calibrations. Here we assume that calibration has been done. Once calibration is done, the primary value of the gain should be 1, but because of many practical difficulties, it can deviate from its principal value. So here I am saying that after the calibration, say gain is 1 plus some small g, which small g is a kind of residual errors. So after subtracting the visibilities, the foreground visibilities from the observed visibilities, we shall get this, where we will left with the 21 centimeter signal component plus a component coming from the residual gain error times the foreground component. And here this component small g times V21, this as 21 centimeter signal is very small, and these residual gain errors are also small. We can neglect these terms over here. So we left with V21 and this g times V foreground. So as foregrounds are very large, even though g are smaller, this g times VFG can still dominate over the 21 centimeter signal. And as we are using these visibilities to estimate the power spectrum, this component can propagate and gives us the biased results of the power spectrum. So we will have the bias in the power spectrum, and these errors will also give rise to the basically enhance the error in the power spectrum estimates. So it is very crucial to investigate the effect of these gain errors and characterize them and estimate their effects in the power spectrum estimators, especially in presence of large foregrounds, which we have in case of epoch of reionization experiments. So there are various foreground removal methods like foreground subtraction and avoidance method, and a lot of efforts has been dedicated in studying these foreground removal strategies. So I won't go into detail of these. So in the right hand side plot we have shown, it is not my plot, it has taken from the Martin et al. 2020. This is the EoR upper limit results from 10 nights of LOFAR EoR observations, where they give the EoR upper limits from their 10 night of observation using LOFAR, and here we find that these limits are well above that the thermal noise limits and the theoretical estimates of the thermal noise. So these discrepancies may arise due to the presence of these calibration errors, which are usually correlated. So now let us discuss the power spectrum estimator which we are using here. So we use visibility based power spectrum estimator. So first what we do, we grid the visibilities in UV space, and to get the power spectrum at certain U, we correlate all the visibilities falling in the grid, and then average over all such grids to get the estimate of the power spectrum at that particular U. Right? This is our power spectrum estimator, and there are various other variants of this estimator which has been discussed already here. Now let us see how many type of visibility correlations we can have. So this region shows one of those grids. So visibilities are actually measured by a pair of antenna, and the signal, electric field signal measured by the pair of antenna is correlated to get these visibilities. So for example, say the visibility measured by antenna pair AB can in real observation can be given by this, where we have decomposed the gains G into the antenna based gains GA and GB. So as Earth rotates, same antenna pair measures multiple visibilities, right? So and one antenna pair basically tracks elliptical traces ellipse in the UV plane and giving rise to different visibility measurements. So say for example, this track is measured by the antenna pair AB, where different dots shows the different visibility measurements at different time stamps. And there will be other antenna pairs like CD and AC. We can correlate all these visibilities to get the estimate of the power spectrum. So for example, we can correlate this visibility with this one, and this one, and this one. All possible cases can be done, except that we don't correlate the visibility with itself to avoid the positive noise bias. This technique is basically known as the nearby baseline correlation. So here we can see that we are not correlating the visibilities at the same baseline. So depending upon the pair of antennas involved in measuring the visibilities, we can have these 4 type of visibility measurements possible. Say we take one visibility from antenna pair measured by antenna pair AB, and another one also measured by the same antenna pair but at different time stamp. So this will be our type baseline. So this will be our type 1 visibility pairs, and again we can have the cases where one antenna is common and the visibilities are measured at same time stamp. In the third case, we can have the visibility pairs where we have one antenna in common but they are measured at 2 different time stamps. And in the fourth case, all other cases false where we have no antenna common. So we define a quantity baseline pair fractions in this way, where Ni is the type of baseline pair fractions which we are talking about. Ni is defined in this way, where this basically the number of baseline pairs of type I divided by total number of baseline pairs in a particular region. Now coming to the systematic effects which we have in the observation. So visibility measured by antenna pair AB, again I have discussed earlier, given by this way. To correct for these antenna based complex gains, we use various calibration procedures like primary calibration, self calibration, and to correct the frequency response of the gains, we use a band pass calibration as well. So here we haven't shown the dependence of the frequency, but gains also depends on the frequency. As I earlier mentioned, that we assume that calibration has already been done. So after the calibration has been done, these antenna based gains can be given as 1 plus some residual component in the residual error in the amplitude of the gains, and this phi here is the residual phase error. There are various regions of gain errors. We won't go into details of the reasons of these gain errors. So without referring to particular reason of the errors, we model the gain errors in the following way. So we model the antenna based gains for antenna A in this way, where delta AR is the real component of the residual gain error, delta AI is the imaginary component of the residual gain error, and to incorporate the time correlation of the gain errors, we model the time correlation using a Gaussian function, and the half width of this Gaussian will give us the correlation time. So I also said that we will be subtracting the foreground. So for that we choose the point source foregrounds in our study. So basically that point sources can be very accurately modeled compared to the galactic diffuse synchrotron emission. So we can directly subtract these point source foregrounds from the visibility itself. Here in this part we assume that there is no frequency correlation. I mean, we haven't considered the frequency dependence of the gains at all, and we assume that antenna gains are not correlated across different days of observation. Further, the cross antenna gains and real and imaginary components are also not correlated. In practical, this may be possible, but here we assume that they are not correlated. So we, using these gain error models and having a foreground model, we propagate these errors and calculate the bias and the error in the power spectrum. We, after doing some hard work, we find these analytical expressions for bias and variance. Here this BP shows the bias in the power spectrum. Here we find that basically this PF is the point, the foreground power spectrum, and this comes from the gain error model. ND is the number of days of observation. We find that basically these effects decreases with increasing observation time. Here N1, N2, N3, etc. are the baseline pair fractions I discussed earlier. We find that mostly the major contribution comes from the baseline pair fractions of type 1 and type 3. This chi is the overall effect of the time correlation of the gain errors. Similarly, this is the expression of the gain errors. In absence of no gain errors, we will have this much of the gain errors, this much of the errors in the power spectrum. But because of the presence of gain errors, we get additional contributions to the error. Detailed calculation can be found over here. Okay. So once we have the foreground model and the baseline pair fractions of the telescope which we want to calculate, I mean use for the observation, we can estimate bias and error in the power spectrum. So first we took GMRT, and for GMRT we estimated the baseline pair fractions for realistic observations of 8 hours, and we have used these parameters to calculate the baseline pair fractions. So this shows the distribution of baseline pair fractions with you. Here we find that baseline pair fractions of type 1 dominate in case of GMRT, and others are significantly lower compared to this type 1. So we have these analytical expressions to validate our analytical results. We perform the simulation using GMRT over 128 relations of gain, error, noise and foreground, and validate our results from the simulations. So here we see both the results. These thicker curves here and here shows the results from the analytical expressions, and the thinner curves shows the simulation results for various parameters like sigma I, error in the gain, say to be 1% and 5%, and we kept fixed these parameters. So we find that we have kind of a good agreement between the analytical results and the simulations. Similarly, in this here right hand side we show the similar results for the error in the power spectrum. So once validated through the simulations, we use these analytical results for further analysis, analyzing the effect of the gain errors. So here what we see, we wanted to check so for a particular gain error model how much time it will be required, okay, to detect the 21 centimeter signal. So with the gain error model discussed here with 16 megahertz of bandwidth, and so these parameters like correlation time is 16 seconds, we find that approximately for 400 days of observation we can detect the 21 centimeter signal, as the error also will be lesser than 21 centimeter signal. So this gives us a rough estimate where we have chosen the errors in the gain to be 0.1%, that is quite low. So these results are very much dependent on the our models. Here what we plot that we define a quantity called risk, which is defined in this way, where a bias risk is defined in this way, which shows the combined effect of the bias and error in the power spectrum both. So for smaller gain errors, these parameters are for 0.1%, and these curves are for 1% of gain errors. We find that for smaller gain error values, risk basically follows the error in the power spectrum, and for higher gain errors, initially it follows the error in the power spectrum, then it follows the bias in the power spectrum. So here we can see that for a particular particular observational parameters will have minimum risk. Minimum means kind of lower risk compared to other parameters. So using these results, we can choose our optimum observation parameters. Okay. So after that, we incorporated the frequency correlation of the gain errors in our studies, and again we model the frequency correlations of the gain in the similar fashion as we model our time correlated gains. And again we use for frequency correlation, we use the similar Gaussian function, and we again did the similar job in presence of both time and frequency correlated gains to have an estimate of the bias and variance in the angular power spectrum. So these are the expressions. Again, these are the things what we have given. I mean, all the expressions have been given here. So as we use these analytical results for further analysis of these analyze the effect of gain errors for, in this case, SKA1 low, because we will be ultimately focusing on that. So in this plot, we again show the baseline pair fractions for SKA1 low with these observational parameters, and we find that in case of SKA1 low, opposite to the GMRT, type 4 baseline pair fractions of type 4 dominates where no antenna is in common. So these are our other analysis, I mean, parameters. So here we plot these bias and error in the angular power spectrum for different set of parameters like correlation length of the frequency and different amount of gain errors. So we find that so this is, for example, for air the error in the gain is 1%, and for this curve this is in the say 0.1%. So we find that for higher gain errors, obviously bias and also error will be higher. So if also we find that if the correlation in the gain errors are larger, we will have larger values of the bias and also error will be large. Here we did not see much deviation in the error expressions, I mean error results, because that is mostly dominated by the thermal noise component here for these particular values. So here we plot the similar thing but with the error in the band pass gains, and we find that this both the things monotonically increases with increasing gain errors. So as I mentioned, these things introduces some bias and enhances the error. So what can be the solution? So from the analytical expressions, we saw that major contributions come from the type of baseline pair fractions which involves at least one antenna in common. So majorly type 1 and type 3. So what if we remove type 1 and type 3 from our observation? What will happen? So this is again the older plot which I showed 2 slides back, and this is the again plot of the bias and error, where we haven't included the effect from baseline pair fractions of type 1 and 3, and here we find that this reduces bias significantly compared to the previous case when we have all type of baseline pairs. Here we find that the error is not decreasing much, but that's fine here, but this bias can be decreased significantly. So this can be a possible solution. Still we are working on finding, I mean, even better things. So again, just to compare the performance of the SKA1 low and GMRT, we estimated this bias and variance for GMRT with their optimum observational parameters, and for basically different days of observations. We find that basically these green curves are, these green lines is the EoR 21 cm power spectrum model taken from the Bharadwaj et al. 2005, and this is the 3 sigma level. So we find that SKA1 low will take approximately 50 times lesser time compared to GMRT with these gain error models which we have used here. I mean, in real scenario results can be different, and that they will be different also. So this is basically due to the baseline configuration of the SKA1 low and having larger collecting area compared to GMRT. So to summarize, so presence of frequency and time and frequency correlated gain introduces bias and enhances the power, enhances the error in the power spectrum measurements, which uses visibility correlation based estimators. And then we develop an analytical framework to estimate these bias and variances. And as expected, basically both bias and error in the power spectrum will increase with increasing amplitude of the gain errors as well as the correlation of these gains. So if we remove baseline pair fractions of type 1 and type 3, there is significant decrement in the bias. And this framework, this is the analytical framework to estimate the bias and variance. So this we can use for any telescope, any gain error model, and any foreground model. Given that we can subtract the foreground directly from the visibilities. So having this, we can, prior to the observation, we can estimate this bias and study the further other effects of the gain errors without performing the full simulation, which will obviously without full simulation, and which will reduce the our computation time. As well as prior to the observation, we can perform these analysis for that particular telescope and have this optimum observation parameters which we should choose to get the better results in, to avoid these bias and errors. Thanks.
So thank you, Jayesh, for your confident and timely delivery. So we can take a few questions now. So, any questions? So then we'll meet again after tea break at 12:05.